Welcome to the Explainer. Today, we're going to tackle one of the most fundamental rules of the entire universe. Seriously, it governs everything, from the engine inside your car to the very energy your brain is using to process what I'm saying right now. So let's kick things off with a classic thought experiment, one that has absolutely captivated inventors and dreamers for centuries. Could you build a machine that just runs forever on its own? A perpetual motion machine. A device that could work indefinitely without needing any fuel. Just imagine a car that never needs gas, or a phone that never needs charging. It sounds amazing, right? But there's a catch, a big one. The universe has a very strict, non-negotiable rule that makes a machine like this completely and totally impossible. And understanding that rule, well, that's the key to understanding how pretty much everything in our world actually works. And that rule is exactly what we're here to explore. It's known as the First Law of Thermodynamics. Now, I know that sounds a little intimidating, but it's not just some obscure bit of physics. It is quite literally the ultimate energy rule for the entire cosmos. So what is this law really? At its heart, it's an incredibly simple but really profound statement. Energy can't be created out of thin air, and it can't be destroyed. It can only be transformed. The total amount of energy in a closed system, and you can think of our universe as the ultimate closed system, is constant. It's always the same. All you can ever do is change its form. And this isn't some newfangled idea. Some of the greatest minds in history have wrestled with this. Albert Einstein, for one, famously summed it all up with this powerful quote you see right here. It just perfectly captures the whole essence of the law. To really wrap our heads around this, let's think of the universe as having a super strict energy budget. It absolutely cannot overspend, and it can't just print more energy when it feels like it. It can only move its assets around. So let's take a look at how scientists actually track these cosmic transactions. Okay, this simple-looking equation is how scientists put the law into practice. Let's break it down real quick. That triangle U, or delta U, that's the change in a system's internal energy. Think of it as the total energy stored inside something. Q is the heat you add to it, and W is the work the system does, like an engine pushing a piston. So all this is saying is that the change in the total energy is just the heat you put in minus the work it puts out. Simple as that. The books always have to balance. Let's stick with that budget idea for a second. Think of the internal energy as your bank account balance. It's what we call a state function, which just means that only the final amount matters, not really how it got there. But heat and work, they're like the individual deposits and withdrawals. They're path functions because the specific transaction, the path you took to get there, actually matters. The law keeps track of both the final balance and all the little transactions along the way. Now, this whole understanding didn't just appear overnight in some eureka moment. It was built piece by piece over decades. It kind of started back in 1824 when Sadi Carnot first suggested that maybe heat and mechanical work were connected. Then, in 1845, a guy named James Prescott Joule proved it with experiments. And finally, by 1850, scientists like Rudolf Clausius and William Rankine put all the pieces together into the law we know today. All right, theory is one thing, but what makes the first law so cool is that it's not just an equation on a chalkboard. It is happening all around us, all the time. So let's see how this cosmic rule actually governs our daily lives. We're going to look at a few fantastic examples, from the engines in our cars and the refrigerators in our kitchens, all the way to the simple act of cooking a meal, and even the very metabolism that's keeping us all alive right now. Okay, let's start with your refrigerator. Ever wonder how it works? It doesn't actually create cold. That's not really a thing. It's an energy mover. A liquid refrigerant absorbs heat from inside your fridge, which makes it turn into a gas. Then a compressor squeezes that gas, making it super hot. That hot gas then releases all its heat through those coils on the back of your fridge. As it cools, it turns back into a liquid and is ready to start the whole cycle over again. It's just moving heat energy from the inside to the outside. No energy created, no energy destroyed. And it's not just machines. You, yes you, are a walking, talking example of the first law in action. When you eat food, your body is busy converting the chemical energy stored in that food. That energy gets transformed into heat to keep you warm and into kinetic energy for every single move you make. You are a living, breathing, thermodynamic machine. Believe it or not, Even something as ordinary as cooking is pure thermodynamics. When you bake a cake or fry an egg, you're adding heat energy to cause chemical reactions. You're transforming the raw ingredients into something totally new and, hopefully, delicious. It's a hands-on energy conversion experiment you probably do every single day. Okay, but here's where it gets really interesting. Here's the plot twist. For all of its incredible power, the first law has it has some blind spots. It tells us the universe's energy budget is always balanced, but it doesn't tell us everything about the transaction. There are a few really big questions the first law just can't answer on its own. For one, it doesn't tell you if a process will even happen spontaneously. It also doesn't specify the direction of that process. And it says absolutely nothing about how efficiently you can convert one type of energy into another. Think about this for a second. We all know that a hot cup of coffee left on a table will cool down as it transfers its heat to the room. The first law is totally cool with that. Energy is conserved, it just moved. But here's the thing. According to the first law, the reverse should also be possible. Energy would still be conserved if heat from the room just spontaneously flowed into a cold cup of coffee, making it hot. But we know intuitively that never ever happens. So why not? Well, to answer that question, you need another rule, the second law of thermodynamics. It's all about the arrow of time and a fascinating concept called entropy. But that is a whole other explainer for another day. So, after all that, you might be asking, okay, why does this really matter? It's not just some abstract idea for physicists. This one rule is literally the foundation of our modern world and, more importantly, the key to our future. You know, every single time an engineer designs a more fuel-efficient car, or when scientists develop better solar panels or wind turbines, they are working directly with the first law. It's the fundamental rulebook. Since we can't just create new energy out of nothing, the law forces us to get smarter and more creative about how we transform and use the energy we already have. I love this quote from the ecologist H.T. Odum. He said, "Energy is the currency of nature." And if that's true, then the first law of thermodynamics is its most basic banking principle. There's a fixed amount in the universal account, and our job is to figure out how to manage it wisely. So that leaves us with one final, really important thought. This law doesn't just describe how the universe works, it kind of hands us a profound responsibility. Since we can't create new energy, the ultimate challenge for us is learning how to spend the currency we have more wisely. And honestly, how we answer that question is going to define our future.